What's up, folks? So today we're going to derive the full SDXL objective. So it's going to build off of the last two videos where I derived the closed form solutions for the forward process and the reverse process. Well, the parameters in the reverse process and the parameters for the forward process. And today I'm going to derive the full objective, which is going to use those closed form solutions. So usually what I've been doing is I've been writing the math out like in real time, but I think I'm going to change the format, which is going to help me get more content out faster. I'm just going to use my notes and I'm going to use a laser pointer in this app to just show you exactly, to just talk you through the steps that's in my notes. I can move a lot quicker this way. This derivation has quite a few steps, and yeah, I just want to get moving on this. So I don't know. I don't really think writing it out buys me anything other than it just looks like a flex. You know what I mean? Which I don't know. I think it'll. I think you can learn. You can learn either way. I think you just following along as I'm showing you how what I did in my notes is equally as powerful. So yeah, let's get started with that. So okay. Once it hits 30 minutes, I'm gonna stop the video. Well, I'm gonna try to wrap up wherever I am. Just, like I said, I want to release more content more frequently, and yeah, just make the process a bit more streamlined. And I think splitting it into parts will aid in that. So okay, let's get started. So okay, we're gonna derive the full SDXL objective. If you watch the video on the closed form solution to the forward process, you will see how I started the derivation. So I'm going to move through the beginning maybe a bit more quickly, and you can go back to one of the forward process video if you want more detail on the objective function. But for the steps, we're going to define the modeling objective, introduce the forward process. We have to introduce the known forward process, which we derived already in order to do variational inference and get the elbow, the evidence lower bound. And then we're going to start decomposing. This loss right here to move towards this final decomposition before we get the weighted MSE version of the loss that you see in the Stable Diffusion XL paper. Okay, so let's get started. So we're going to define the modeling objective, right? So just like in every single, in most ML objectives, right? Especially in generative modeling, well, just generative or discriminative, the objective is always to maximize the likelihood. That's what this is. We're finding theta that maximizes the likelihood of the data. X naught is our image, and so for each image in the data set, we want to maximize the log likelihood. Okay, that's what we want to find, the theta that maximizes this log likelihood. That's our modeling objective. Okay. So now we're going to look at we're just going to look at this right here without the log. We're just going to look at a single data point. And we're going to try to expand this. So we're going to first I need to show you why this is intractable, why it's unsolvable, and then we're going to introduce a known forward process. Okay, so this probability, the probability of the data of this single data point, which is a flattened image vector, is the marginal probability, right? So remember, this is a latent model where we have latent noisy images from xt to x1, right? T being full noise, x1 being the image right before the original image, right? And we want to gradually denoise this image to x naught in order to, expose this generated image, right? So I think in the literature, you'll see this as x0 to t, right? That just means, so x0 to t just means x0 to t just means x0 to xt, like comma, 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 right? It's just that set. This is just shorthand notation, right? So this is a bunch of integrals here that we have. It's an integral for each latent variable. And, right, so x naught is our original image. And so this is a marginal probability over all the intermediate noisy images from xt to x1. The reason why I'm doing this from t to 0 instead of from 0 to t is just to show you that we're going from t, we're doing the denoising process, right? Where we have a really noisy image to a clean image, right? You'll see it as x0 to t, but I don't know. I just think it's a bit more clear when I do xt to 0, so you can see the directionality. So, right, that's this marginal. So this is essentially we're marginalizing over all latent trajectories that could lead back to the original image x naught. So, right, so as I showed in my previous video, that's equal to this distribution, right? Because of the Markov assumption, right? We just use conditional probabilities to expand this, and then we use a Markov assumption to get this product right here. So t minus 1 only depends on t. That's the assumption we're making to simplify things. So this kernel, right? How do we get, a slightly less noisy image from a noisy image? That kernel is unknown. If we knew that, our problem would be solved, right? So what we're going to do is we're going to introduce this known forward kernel, which we derived in the previous video, which has these parameters, okay? And so we needed to get these parameters in order to get to the L2 norm form of the loss that we're going to show at the very end of this derivation. So we introduced this known forward process, right? So now I'm going to rewrite this probability here, and I'm just going to introduce that known forward process as an identity, meaning I'm going to multiply and divide by it, right? And then I add the log, right? So now this marginal probability just has this product in this denominator. And then remember, we defined this as this. So now I just expand it. This in the integral, right, means this is an expectation under this, right? So we turn it into an expectation. The log stays outside of the expectation, and then this is the known for it, right? We're just swapping this and this, okay? So now Jensen's inequality says that f of an expectation of x is greater than or equal to the expectation of f of x for a concave f, right? So log is our f, so log of e is greater than or equal to e of log by Jensen's inequality, right? And then we use the properties of log, right? That's why we always do log likelihoods in machine learning. So now that's log of this plus log of this, which makes this a sum, minus log of this, and if we bring that through, it makes that a sum. So we have log of this plus this minus that, right? So that's our elbow loss. So if we maximize this, we know we're saying that that's always going to be greater than or equal to this, right? So we know that if we maximize this, we're maximizing that as well. So okay, so now we're going to start decomposing this. So I made this salmon color B, and this term this light blue color C. Okay, so this is B minus C right here. Okay, I'm just writing that here. So now we're going to group terms. We're going to group these terms. I'm going to collect all t equals 2 to capital T, and then I'm going to collect all t equals 1. So this is all t. I'm just splitting this. I'm just removing this from the summation, and then that becomes t equals 2. So that we just reindex. I'm just removing this and reindexing, okay? Now I bring the expectation. So remember, there's an expectation around all of this. So I can bring, expectations are linear functions, so I can bring this through, right? So if I bring this expectation here and bring it through, all right, I'm just gonna bring the expectation around this and then the expectation around this, and I rewrite the loss here, okay? I'm gonna call this loss, this form of the loss, G. We're gonna keep decomposing this. I'm gonna call this inside the expectation G.1. And remember, Q right now is defined as this known forward process, right? So this loss is an expectation under the known forward process. Think about that, right? This loss is an expectation under the distribution of a forward process that we know, right? That's what allows us to do this derivation. Or yeah, the loss is defined as a lower bound on a process that we know, that we've defined, right? Which is going from a clean image to a slightly more image to more noisy to complete noise, right? We're defining the expectation under that distribution. Okay, so now we're gonna look at G.1, this little piece right here. So, okay, so this is this right here. Now I'm gonna insert a posterior identity. So this is the posterior, and I just call it an identity because I'm adding it and subtracting it, right? So that's why I can just introduce this in here and then group this and group this, right? So this is this, and this is this. And then I'm just inserting the posterior identity between. I'm gonna call this B.1, and I'm gonna call this B.2. Okay, so now this expectation is wrapping this in this. Now, what I'm gonna do now to the salmon colored one is I'm gonna show, if I were to take this expectation right here, right, because expectations are linear functions, what does this whole thing turn into? I'm gonna show you what this turns into. Well, I'm gonna show you right now that turns into this, right? So the expectation, so remember Q is this expectation of Q, right, of B.1, this is gonna be equal to the expectation of this, right? Which we know, we've defined this distribution of this negative KL divergence. So how do we do that? Okay, so first, I'm gonna call B.1, I'm gonna define it as F. F of X, T minus 1, and XT. Indexed by, right, so F of X, T minus 1, and XT, right? I'm just gonna define this placeholder. So now the expectation of B.1 is this. Now we know expectations are integrals, right? And it's an integral, right? We just under, right? So it's weighted by this distribution. So we bring this here, and then we just do dx 1 to t, this forward process, right? And it's an integral for each variable x1 to x sub capital T, okay? Now f only depends on these two variables, right? So all the other variables of x1 to all the way up to t minus 1 and xt, all those other variables we integrate out. And what we're left with is, so all those integrals remove and all the variables from here remove except for these variables, t minus 1 and t. That leaves us with two integrals, okay? And this posterior distribution. right? Because, right, only these are left in the distribution. So they're conditioned on x naught. How do we get xt and xt minus 1? We know how to do that, right? So now we know this identity. We've been over this identity in the previous video from Bayes' rule, okay? And so we're gonna swap, we're gonna put this right here. And when we do that, we're gonna pull this outside of, we're gonna group these two integrals. The first integral is gonna be of everything that includes the variable dx t minus 1, right? And then we're gonna pull this one out, and then, right? So we're just separating the two integrals, this one and this one. So we do this integral first, and then we can do this integral, which depends on dx sub t. So this, right, weighted by this posterior, it's just this expectation, right? So we bring this posterior, so this is the expectation under this posterior of f of x t minus 1 xt, right? And then, right, so that is, so then we just, what's f of x? So what is f? It's this. It's log of p theta, it's log of p theta divided by q, it's log of p divided by q, right? It's log of this minus log of this, which is just division. So we just swap out f with its original definition, right? So we get the expectation of f, which is this right here. Now the definition of KL divergence is expectation of x distributed according to p. So all x distributed according to p, log of p, wait. Okay. So we know that the definition of KL divergence between P and Q is equal to the expectation under P of log of P divided by log of Q, right? So expectation, so here we can see the Q should be on top if we want true KL divergence, right? But it's switched with the bottom, right? So this is just negative KL divergence, okay? So this is equal to the negative KL divergence, right? So this is equal to the negative KL divergence, right? But it's still this integral, it's still wrapped around this, it's still inside of this integral, right? Which we know it's an expectation weighted by this, right? So this entire thing is the expectation under this Q of the negative KL divergence, right? So this, we started with this right here, and we're trying to break it down, is equal to this, is equal to this. Okay? So that takes care of, if we were to, so this, okay, so this expectation under Q of all of this, right? We expand the inside, we expand these logs, we add the identity and expand it. And then what if we were to take just the expectation under Q of this? That whole thing, including the expectation under Q, turns into this. So now we're gonna look at this part of it. And we're gonna look at it without the expectation. I sort of messed up the flow in my notes, but it's okay, I'm not redoing all this. You should be able to follow along. So here we're looking at it under Q, here we're not looking at it under Q for now. We're just looking at, I'm just gonna break down this and then I'm gonna add in the expectation later. Okay, so, okay, this is B point 2, okay? So what is this? we use Bayes' rule to expand it to this, okay? We went over this in one of the previous videos where we make a Markov assumption in the forward process, so this x naught goes away. We don't need that. We only need the previous noisy image. Okay, and so we rewrite that as this. Now it's wrapped. So right, so this is equal to this. So now we just include the log, and then it becomes log of this plus log of this minus log of this, which is here, right? And then we include this term, boom. And now this cancels with this. So this equals this. And that's what I've written here. Now we still need to bring in the expectation for this specific part, which I'm gonna do, which I do here, right here. I wrap this in the expectation like it's supposed to be, right? So here's the loss before we do all the substitutions. So that should be, right. So I just copied and pasted this loss, G. So this is G. You can see in my notes, I'm saying now back to the loss, right? Now back to G. We swap in, well, I've already showed you I've already showed you how we get this. And now I'm taking this and I'm putting that and I'm bringing the expectation through. So I expanded what was inside of here, and then part of it became this. And then now I'm taking the other part of the log and I'm bringing the E into it. It's a little bit disjointed how I did it. I apologize, but you should be able to follow what I'm saying. I hope you can. I hope you can follow what I'm saying. Okay, so this now becomes this. Now this I'm gonna telescope. So essentially I'm gonna remove, this sum and this indexing, and I'm just gonna expand the whole thing out, okay? And what happens is when you expand the whole thing out, you'll find that everything in the middle cancels, all right? So this telescoping sum results in cancellation of everything in the middle, and you end up with the two extremes, all right? So this equals this and this, or this minus this. And now I'm also going to distribute this expectation through here. So I distribute this expectation through, and it becomes these two separate terms. And then this becomes these two separate terms down here. And then this ends up canceling with this. So now we have this, 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 and this, these four terms. Right, which I rewrite everything here nice and neatly. And so this is the final decomposition. Oh yeah, right. And so, okay, right. So we have these four terms, and now I pair this with this. Wait, this isn't right. This isn't right. This isn't right. Plus this. Okay, that's right. I'm gonna redraw. Actually, let's. Whoa. Okay. Okay. All right. Okay. So after we cancel these, we're left with these four terms. And then I group this expectation and this together here. And that becomes this KL divergence right here. And then I just bring this term down here. And I bring this term down here. And this is the general form of the stable diffusion XL loss. And depending on what version of the forward process you use, you will come up with, well, as long as your forward process is a Gaussian of some sort, whether you're using a cosine schedule or a linear schedule, there's a bunch of different schedules, but I'm pretty sure it always was. I'm pretty sure this term always resolves to be the squared L2 norm and all these different variations of your loss function. Let's see how we're doing on time. Yeah, I'm almost at 30 minutes, I think. So yeah, I think this is a good place to stop. So let's do a review just quickly. So we define the modeling objective. We find that this reverse process is unknown, right? If it was known, our problem would be solved. It's unknown. So we introduce a known forward process going from a clean image to a completely noisy image, right? We already got the closed form solution for this in terms of DDPM if we're using a linear schedule. And we introduced that known forward kernel as an identity. And then we use Jensen's inequality to find the evidence lower bound. And then we get this form of the loss function, okay? And then we start decomposing the loss function, just doing some algebra, which I personally think it's important. That's why I'm doing all this. If I didn't think it was important to know, as a first principles guy, then I wouldn't be doing this. So we do a bunch of algebra. I think the interesting thing to know is how this marginal probability, this marginal distribution, given that when we have these variables x1 to xt, we integrate out all of the variables that neither of these this function doesn't depend on, right? And since if that's the case, then we can change what this is an expectation under. That's the point. And so it becomes an expectation. So once we bring in this expectation as well, and we have this right here. This is the full thing written out. This becomes an expectation So this becomes the negative KL divergence, and then this entire thing becomes this expectation of the KL divergence. And then once we handle the other part of this, what was inside the expectation here, we can come back to our original loss, expand everything out with our replacements. We telescope, we find that everything cancels. So we can rewrite this as these two. We find that we have these cancellations. We group this with this here, which turns into this KL divergence. And then we bring this term through and this term through. And this is the general form, the general decomposition of the loss function. Okay, let's stop it here. So next in the next video, I'm gonna continue and show you how we get how that turns into the squared L2 norm between the true noise vector and the predicted noise vector, as you'll see in Stable Diffusion XL. So thanks for watching.